Okay, hi. Thank you. I'm going to talk about eMMC hacking, or what can you do with eMMC chips, and how I fixed bricked Galaxy S3 devices. So a quick introduction about myself. I am Oran Avraham. I'm 25 years old. I'm a security researcher based in Israel. I currently work for a company called Medigate. I previously worked on OpenIBoot, which was an open source project for developing an open source alternative bootloader for Apple iOS devices. I also found some vulnerabilities in the iPhone 3G, 3GS, and iPhone 4 basebands, which were used to SIM-free these devices. And I'm also a CDF player with PAS10. And this is my contact info. You can find my website, and then you have my Twitter handle, so make sure to follow. Okay, so a quick outline about the talk. I'm going to start with introduction. Then we'll talk about Samsung's eMMC patch, and we'll discuss later what does it mean. Then I will discuss how I obtained and analyzed the firmware of such eMMC chips. Then we'll discuss the bug itself that was in Galaxy S3 devices. And then I will show how I'm resurrecting dead phones. So, introduction. This phenomenon was called sudden death syndrome. And it started around 2012. Samsung Galaxy S3 devices, this specific model, GTI 9300, started dying with no apparent reason. So it's basically you could use your phone, and then one day it won't turn on anymore, and it's just a brick. If you're lucky, the phone will actually boot. You will see some screen, but it won't continue afterwards. And if you're not, you can't do anything. You can't plug in a USB cable. You can't. It's just a brick. And I used to own an S3 back then, and I was somewhat afraid. My phone didn't die, but yeah. And there was a lot of rants in forums. So this is an example. Somebody said this is a screenshot from XDA developers. Somebody said this is happening to a lot of people. I hope Samsung do something about this. And actually they did. But it wasn't like a proper fix. And I will show why later. So how do you diagnose such a dead, like a bricked S3? So this is a working S3. You can see like the phone. You have a beautiful background and everything. And then this is a dead one. No, it's just a brick. You can't do anything. You try to turn it on and nothing happens. And as I said before, if you're lucky, you'll get to this screen, which is the bootloader of S3 of Samsung phones showing something on the screen. This is called S-Boot. This is the bootloader they use. And but it won't load. It won't boot Linux or Android afterwards. And if you can get into the bootloader, then if you press a specific combination of keys, you'll get this screen, which is called download mode, which is used for flashing your phone with new firmware, but it won't work. If you try to flash it, it will get stuck, and I will discuss later why. Okay, so this is my current understanding of how Galaxy S3 works. You have the main CPU, which is called Samsung Exynos. It's an ARM-based CPU. And it basically runs all the software that you can see on the phone screen. So it runs Android and all the apps and basically everything except for the communication, the wireless communication. And then you have the eMMC chip, which is the storage chip of the phone. And there is a NAND flash inside the eMMC, according to the eMMC specification. And this stores all the data that the phone needs, including the software. So one day, Samsung dropped a patch. And when I say dropped a patch, I mean that they talked to the media and they said, we fixed this issue with Galaxy S3 phones. And they published a new firmware. And since it's based on Linux, they had to publish the source code because it's GPL licensed. So this is like the main logic of the patch. And the thing to note about this patch is that it resides in the eMMC subsystem or the MMC subsystem. So when I saw this patch, obviously the first thing I needed to do is to understand what is eMMC, right? So eMMC is the standard storage medium for mobile phones. Actually, today, there's a new standard called UFS, but it's only used in higher-end phones. So actually, most of the mobile phones, even today, still use eMMCs. And it's basically an SD card in BGA form, which means that it's exactly the same as SD cards, only it's packaged in a chip which you can solder onto a PCB. So like to prove that it's essentially the same bus, you can see that some company called Hardkernel made an adapter from eMMCs to like SD card form, and you can just plug it into an SD card reader, and it works. So yeah, so when I say later in this talk card, I will refer to eMMCs because it's the same. And the thing to know, the important thing to know about eMMCs is that it's a NAND flash chip wrapped in a convenient bus. So you send commands which are basically storage operations. And how, the internals of the eMMC bus work by sending commands. So if the host wants to talk with a card, it sends a command with a single argument, which is 32 bits. And there are 64 commands, up from command 0 up to command 63. And for example, command 17 is read single block, and command 24 is write block, which is basically read and write operations. And each command takes a single argument. So all the commands are categorized into classes, and there's one particular interesting class, which is class 8, because according to the specification, all the commands in class 8, which are commands 60 up to 63, are reserved for the manufacturer. So if something uses these commands, it might be interesting because it's not something that you normally do. So let's go back to the patch. So this is Samsung's patch to fix the issue with Galaxy S3 phones. And as you can see, it compares some things. It compares the card name to VTU00M, which is the hardware revision of the faulty chip. And then it compares some other number, which is apparently the firmware version of the chip, to F1. And then the other comparisons is not that interesting. And then it calls this function, eMMC start movie operation, which is like the main logic for the fix. And this patch, this code runs every time you boot your phone. And this is not the exact same code, but I edited a bit for brevity. So basically what it does is, I don't know, but there are some interesting things about this function. So the first thing is, why is there an erase? Like every time you boot the phone, it tries to erase some data. It doesn't make any sense. And then when you inspect this function, this eMMC movie erase command, you see that it takes two arguments. The first is the first block to erase, and the other is the last block to erase, and it erases all the blocks in the middle. So if you give it, say, like blocks 10 up to 20, it will erase all the blocks in the middle. And then if you look at the numbers, you can see that it doesn't make any sense because the ranges overlap and the numbers are strange. So my thought was that this probably not a proper erase. It probably does something else. And then the other thing to note about this function is that they use eMMC movie CMD at the beginning, at the end of the function. And this eMMC movie CMD is basically command 62, which is a class 8 command. So it probably does something that Samsung left in the chip. So my guess was that the first two lines enter some secret backdoor mode, and then the last two lines exit this secret backdoor mode. And during this mode, the erase command is no longer an erase command. It probably does something else, which should fix the chip. And then I noticed that all the numbers, if you inspect the first argument being passed to the erase commands, you can see that the numbers are consecutive except for the last number, which does look like memory addresses. And then if you inspect the second argument, you can see it looks like data. And then I noticed something interesting. I used to code some ARM assembly, and the data starts with 10b5, if you look at it as little endian numbers. And 10b5 is push in thumb, which is an instruction set inside the ARM specification. So functions start with push, right? So this probably looks like a function. So I just took all the data that it writes, and well, this is an eMMC next to a thumb, okay? And my point is that there's probably some thumb chip inside. So as I understand it right now, eMMCs have an NAND flash chip and also an ARM chip, which runs the thumb instruction set. And there's probably some firmware inside this ARM chip. So I wanted to know what this firmware does. So I basically took all the data that it writes every time you boot a device, like from the patch, and I dropped it into, just written it to a file, to a binary file, and then I opened it with IDA Pro. And this is Samsung's patch for fixing Galaxy S3 phones. I hope you prepared your C skills. And so at the top, you can see like a C pseudocode. And at the bottom, if you're familiar with thumb assembly, you can see the actual thumb assembly. And basically what it does is it calls some function. And if this function returns 0, it goes into an infinite loop. Now, later on, I understood that the original code that is being patched right here called the exact same function with no checks at all. So basically what I did is they kept the function call, but if it returns 0, it goes into an infinite loop. And my guess was that this secret backdoor mode enables you to write to the eMMC's memory. So my guess was that this can't fix anything, right? Because there was a function call, and now there's the same function call, but in some specific cases, it will go into an infinite loop, which doesn't do anything interesting. And then I read other threads in forums, and I noticed this thread, Ultimate Galaxy S3 Unusual Freezing thread. And somebody said that Galaxy S3 phones are freezing with lockup, screen not responding, and ending up with unusual rebooting and boot looping. And Galaxy S3 keeps freezing every 5 minutes, or 50+ freezes a day. And this fits, because if the eMMC chip now sometimes go into an infinite loop, it won't respond anymore, and the whole phone is stuck. And this is, in my opinion, this phone is not usable. You can't use a phone which freezes every 5 minutes. So I had an S3 back then, and I noticed freezes myself. So I wanted to fix it properly. And so the next step was to obtain the firmware of the eMMC. And how do you get the firmware? So you have a chip. All you can do is ask it to read data or write data. And you have like a special backdoor mode which enables you to write the memory, the internal memory of this chip. So the first way I thought about trying was to just write random memory inside with this backdoor inside the ARM chip, and hopefully my code sometimes runs. And then how do you get responses back? So I thought about, well, you might try to write to different memory locations, and hopefully you'll see something on the eMMC bus, and then you can communicate. But this was my personal phone, and I didn't want to destroy it, so I didn't try it. And the next thing I thought about doing was try to fuzz eMMC commands, see if I can find another backdoor mode, which, I don't know, will give me the firmware. But the last thing I thought about was to just look for clues. So how do you look for clues? You Google. So I Googled these two numbers which enter this secret backdoor mode. And I hope that I will find something else which might shed some light. And I found this patch, which is from a different device. And this patch was called Patch the Firmware of Certain Samsung eMMC Parts to Fix a Bug. And it enters this backdoor mode. So you can see it uses command 62 with the numbers EFAC 62EC and then 10, 21, and 4 zeros. Then it writes memory address 4DD9C, and then it exits this backdoor mode. But there was something else afterwards. So if you continue to read this patch, you'll see this snippet of code, which is wrapped by an if-def called test eMMC firmware patching. And then they use the same command 62 from before, but now the second number that they use is 1021, and instead of 4 zeros, it's 0002. And then they use the same erase command from before with the same memory address, but the second argument is 4. And then they read the data from the eMMC. So my thought was, this might be Samsung's way of reading the RAM, right? Because they use the same memory from before with 4, which might be like the size to read, and then they read some things. So I took this snippet of code and turned it into this snippet of code, which basically just loops over all the possible addresses. And like in each loop, I read a single dword from the memory, and then I write it out into a file. And it's important to leave the backdoor mode before you write into the file, because the actual write operation uses the same eMMC. And I got this file, so I opened it up with IDA Pro, and I got something that does look like a firmware. So this was very exciting, because I finally see like Samsung's firmware for eMMC chips. And these names are not, so the file contained obviously addresses. These names are my own, but it looks like an ARM vector table, which is how firmware is supposed to start. So the next step was to reverse and analyze the firmware. And luckily for me, the firmware contained strings. So it wasn't actually strings, it was a string, a specific string, and it was this one. And it's basically an assert, so it doesn't tell you anything. And so I had to reverse the whole firmware without any strings to begin with. But I could, and it's basically most of the functions. This is a snippet from my reverse process, and most of the functions, the names are my own. So you can see like something like flip bit in somewhere, or memory mapped IO flip 4. But it was like a guesswork, so I guessed what this code should do, and then I understood most of the high-level logic. And I got to the point in which I can understand most of the firmware. So let's talk about the bug itself. And before we talk about the bug, we have to understand what is an eMMC actually. So eMMCs have a software layer called Flash Translation Layer, or FTL, inside the firmware, which is responsible for some tasks, which are some of them. This is some examples. It's not all the actual tasks that it does. But it's responsible for world leveling, which is spreading out writes, so no block gets written a lot, and then it might die because of some behavior of flash chips. And then it also does bad block management and some of the eMMC bus communication. So there's this software layer which has to store data for itself, for it to operate. And the bug was that every time you write data onto the eMMC chip, this software layer, the FTL, has to modify its own metadata, which is saved on the NAND flash chip itself. And the bug was that at some point they had a miscalculation, and a corrupted value was written onto the metadata. And then every time you try to boot the device, the FTL will boot on the eMMC itself, and it will try to parse this corrupted metadata. And since it's corrupted, it will raise a CPU exception, because it will try to access some memory location which doesn't exist. And the default exception handler, in Samsung's case, was to just go into an infinite loop. And if it goes into an infinite loop, the eMMC doesn't respond anymore. So the phone, you try to boot your phone, the eMMC starts, and then it goes into an infinite loop. And the main CPU tries to get the software from the eMMC, but the eMMC doesn't respond. So the phone doesn't boot, and it's basically a brick. And Samsung's patch was something like this. Yeah? Right before you try to write corrupted metadata, don't. Just go into an infinite loop, and no corrupted metadata will get written. So instead of actually fixing the bug itself, they just avoided triggering it any at all. So the next step for me was to resurrect dead phones. But yeah, how do you do this? So eMMCs, dead eMMCs, get into a loop at boot. So you try to power on your eMMC chip, and it will get into an infinite loop. But it does something before. So what happens before? So this is the eMMC memory layout. This is the actual ARM chip inside the eMMC layout, which I grabbed from dumping the firmware on my device. And as you can see, it starts with something which I call the boot ROM. And then at address 40,000, you can see the actual firmware itself. So what is this boot ROM? So I think it's a mask ROM, which means that it's stored in silicon during the manufacture process of the eMMC die. And what it does, it initializes the hardware, and it loads the firmware from the NAND flash chip itself. So the actual eMMC firmware is stored on the NAND flash. And then the boot ROM also has its own machinery for eMMC commands when firmware loading fails. And my guess was that when Samsung produces eMMC chips, the NAND flash is empty. And then when they plug in this eMMC to some reader, there's no firmware on it. So the boot ROM responds, and it enables you to communicate with it and flash a new firmware. So this is a part of the production process. You produce an eMMC, you plug it into some eMMC reader, and then you flash a new firmware onto it, and now the eMMC is good to go. And this is my take on about how S3 works. So you have, inside the eMMC, you have an ARM chip, which has a boot ROM stored in silicon, and then you have a NAND flash, which has the actual firmware for the ARM chip. And when I get a bricked phone, if I could ever talk to the boot ROM, this might be interesting, because I might be able to write a new firmware, which will fix the bug. But the firmware loading actually succeeds. So the boot ROM actually is able to load the firmware. It jumps to the firmware, and then the firmware gets into an infinite loop. So there's no chance of ever talking with the boot ROM, right? So actually, there's this interesting logic. During the boot process of the eMMC, there's a specific function which sets a timer for 35 milliseconds. And if during this time window, an interrupt fires, which is interrupt number 7, I don't know what it means, but if this interrupt fires, it reads a value from memory mapped I/O, and this value is compared to some constant. And if everything if everything fits, then the firmware loading is skipped, and it goes right into this boot ROM recovery mode. So I wanted to trigger this interrupt during this time window. And this is basically the logic of the boot process of eMMCs. So the left column is the normal boot process. So you wait this time window, and then no interrupt is fired. So you load the firmware from the flash, and then you boot it. But if you can get into the right column, then you'll get into the eMMC boot ROM recovery mode. This is what I wanted to achieve. So I had a guess. I guessed that this interrupt number 7 corresponds to some eMMC command, and this value that is being read from the memory is probably the eMMC argument. So just to recap, dead eMMCs, bricked eMMCs get stuck on boot because the firmware gets into an infinite loop. However, right before the firmware is actually being loaded, there's a time window of 35 milliseconds, and during this time window, if you are able to trigger some interrupt, then the firmware, the boot ROM won't load the firmware. It will instead go into some recovery mode. But the phone is dead. You can't turn it on. If you try to plug in a USB cable, nothing happens. So how do you even talk with the eMMC? So one thing you could have done was to just desolder the eMMC and then talk with it externally, but I don't know how to desolder BGA chips. And I didn't want to try it. So the next tip is obviously to talk to the eMMC by some kind of magic, and then access the eMMC boot ROM recovery mode, and from there repair the eMMC, and then your phone is fixed. So I said that if you're lucky, you'll get into this screen, which is Samsung's bootloader for the main CPU, for the Exynos. But how? Because if the eMMC doesn't respond, the actual bootloader is stored on the eMMC. So how does the main CPU get this bootloader? So actually, this is how Samsung eMMCs work. You have, on the NAND flash, you have the firmware for the eMMC itself, and then you have a boot partition, and then you have a user partition. And the boot partition stores only Samsung's bootloader, SBoot, for the main CPU. And then the user partition stores everything else, which is the Linux kernel, Android, your apps, your photos, everything. And when the phone boots, it talks to the eMMC, and it asks it to boot the boot partition, to read the boot partition. And the boot partition has its own FTL metadata, and it's still intact. And then when the bootloader tries to boot Linux, it will try to access the user partition, but the user partition metadata is corrupt, and then the eMMC gets stuck. So a friend of mine, thanks Pini, had a bricked S3, which does load SBoot, so he was lucky. And in his case, only the user partition was corrupted. So this is how the phone gets into this state. And I suspect this is a common scenario, because when you write to the eMMC, you write to the user partition. You don't usually write to the boot partition. Okay, so this is how S3 breaks. The user partition is corrupted, but the boot partition is still intact. And what happens is that the main CPU tries to load SBoot from the eMMC's boot partition, which works. And then SBoot tries to load Linux from the user partition, and the eMMC parses the user partition metadata and then gets into a loop. So if your phone gets into this bootloader, you can access download mode, which I shown before. And it has some device firmware upgrade mode, which is using a protocol over USB. So the phone side is called Loki, and the computer side is called Odin. I guess this is a reference to the Norse mythology. And if you ever flashed your Samsung phone, you probably know this screen, which is Odin software, which is the computer side for Windows machines. And in this protocol, there's no way of sending low-level eMMC commands. You can ask the phone to flash a new firmware, and then it will try to access the user partition on the eMMC, and it will get stuck. And basically, that's it. So I want SBoot to send low-level eMMC commands, but the code isn't there. So how do you do this? So obviously, the next step was to exploit SBoot, right, to achieve code execution on it. So this is some pseudocode I wrote based on reversing SBoot. So you can control this variable isDump. And in the first part, you can see that they read some value from the USB packet, and it's stored in a variable called part, and then they send you back a buffer in an offset, which is basically part times 500. This is a relative read, an out-of-bounds read, because they don't do any checks on this value. And if isDump is 0, it will get to the second part. And in this case, they read a value from which you can control, which is called size. And then it will read it onto this buffer. But this buffer is statically allocated. It is 2,000 bytes. And you can control size with whatever size you want. So this is an out-of-bounds write, and you can run code based on it. So there are two vulnerabilities. And eventually, I found out this is not actually a zero-day. It's patched in newer S-boot versions for newer Samsung phones. But since Galaxy S3 is end of life, it's still unpatched for S3. So if you have an S3 at home, you can boot into S-boot, and my exploit will hopefully work. And the actual exploitation details, in my opinion, are somewhat boring because there's no ASLR, there's no NXBit. It's basically trivial exploitation. And you can find the exploit in my GitHub account. So this is a video I shot. So this is download mode. And then you can see Hello World S-boot exploit by Oran. Yeah. Thanks. But what if it's really dead? I mean, what happens is this? So if you're unlucky, there's no boot partition. And you try to boot a device, and the main CPU tries to load S-boot from the eMMC, and nothing responds. So apparently, in this case, there's actually a second boot ROM stored inside the main CPU, the Exynos. So what happens when you try to boot a device? The Exynos boot ROM runs on the main CPU, and then it tries to access the eMMC in order to load S-boot, but the eMMC doesn't respond. So let's see what this Exynos boot ROM does. And apparently, some people over the internet found that if the boot partition is corrupt, if it isn't able to load S-boot from the eMMC, it will go to the external SD card instead and try to load S-boot from the external SD card. So if you have a completely dead phone, you can just prepare S-boot on an external SD card, plug it into your phone, and then it will boot S-boot. And from there, you can exploit it and run your own code. So no hardware mode is required. So to recap, if the boot partition is still intact, the phone will boot S-boot. And if it's corrupt, you can plug in an external SD card, and then it will load S-boot from the external SD card. And in either case, you can exploit it and achieve code execution on the main CPU. And from there, you can probably fix the eMMC. So the next step is to access the eMMC boot ROM. So when you actually exploit S-boot, the eMMC is already in an infinite loop because S-boot already tried to load things from the user partition. So you have to. So what I want to do is just to reboot the eMMC, and then during the time window, send this interrupt, trigger this interrupt in order to interrupt the boot process. So I tried this algorithm in a loop for all the possible commands, up from command 0 up to command 63. So the first step was to power off the eMMC, and then you power it back on. And then you quickly send a command with this argument. And then you wait some time for everything else to finish. And then you send any command supported by the boot ROM, and then you see if you get a response. And I ran this code. And I ran it for command 0, and it failed. And I said, nah, it's never going to work. This is just a guess. And then I tried command 1, and it worked. So I was lucky. And this is very exciting, because this is the first time I had a bricked S3, which I was able to talk with the eMMC. Up until then, I tried various other methods, and every time I didn't get any response from the eMMC. This is the first time the eMMC actually responded. And the eMMC boot ROM even has command 62, so you can read and write the memory. And you can basically do whatever you want. So let's fix it. So how do you repair eMMC chips, like broken eMMC chips? So there were 2 revisions of the faulty chip. The first had firmware which is called F1, which is buggy, and then Samsung released a new chip which had firmware F7 in which the bug was fixed. But they didn't release any tool to update the firmware from F1 to F7. So my goal was to update a broken chip to firmware F7 and then format the all FTL metadata to get like a brand new chip. And the first thing I had to do is to obtain this firmware F7 because I didn't have it. And I wrote some kernel module which dumps the firmware out of your eMMC if it's working. And I published it online. And somebody was great enough to actually run it on his own personal device. And he sent it to me. So I got F7. And thanks to Artesia, which agreed to run my experimental code. And now the next step is to upgrade the firmware on the broken chip. So I could have used like the backdoor to write the eMMC RAM and run my own code. But there was actually a simpler way. So when I reversed the boot ROM, I noticed that there's a command, command 60, which is another class 8 command, which exposes 2 firmware upgrade modes. And the former one, the first one, supports FTL metadata format, so it does basically everything that you need. It formats the FTL metadata, and then it writes a new firmware. So this is how you fix a phone. So let's recap. You get a dead S3. You boot to SBoot either directly if it's semi-bricked or from the SD card if it's completely bricked. Then you exploit SBoot to run your own code. And then you reboot the eMMC into boot ROM recovery mode to be able to talk with the eMMC. Then you use command 60 to format the FTL metadata and to flash a new firmware. You reboot the eMMC, and now the eMMC is empty. It's working, but empty. And then you write SBoot to the MC boot partition, and then your phone should be working again. And the last step is obviously to profit, which means it's demo time. Yeah, so everybody cross your fingers. OK, so if we could move to the camera. OK. So this is, yeah. Let me just put in a battery. Yeah, OK. So this is a bricked phone. I personally bricked it right before the talk. I will try to boot it. Nothing happens. Yeah, I'm trying to press the power button. Believe me, nothing happens. So if I will just plug in this SD card, this SD card contains SBoot, and it should boot it from the external SD card. OK, so it just ran SBoot, and there's no graphics. So the screen shows some interesting patterns. But now I will plug it into the USB. And if we could move to the to the computer. Can we display the computer on the? OK, thanks. I'm going to run this, which runs the exploit. And it will flash firmware F7. Yeah, so the shellcode started, and it should take a couple of seconds. Probably, so it's actually more around a minute or so. So it rebooted the eMMC into boot ROM mode, and now it's got into firmware upgrade mode, and it will flash the firmware. And as soon as it flashed the firmware, it will update the metadata. And now it reboot the eMMC into the firmware, and it will format the partitions inside. OK, so the shellcode is done. And yeah, can we move one more time to the camera? Thanks. So I got a second SD card, which should write sboot onto the boot partition. So where did I put the battery? Okay, yeah. So now the device should boot into this SD card. Should take a couple of seconds. Okay, yeah. So this was SD card mode of sboot, and now there's no SD card inside. I just plug it outside, and the device should be fixed. So if I plug in a battery, then I press this specific key combination, it should get into sboot. Yeah, okay. So the phone is fixed. Thanks. Okay, can we go back to the, yeah, thanks. Okay, so this was a live demo of how I fixed an S3. And yeah, let me just, okay. So conclusion. So this is old eMMC chips, and I wanted to know if this is still applicable to newer eMMCs. This is an ongoing research, so take it with a grain of salt. But it's still fresh. So I just went over pictures of Chinese development boards and tried to spot some picture with Samsung eMMC soldered inside, because I didn't have enough resources to buy all the development boards and do it myself. And I found this board, which is called Orange Pi Plus 2. And if you look at the picture carefully, you can see this chip. I think this is the original resolution, but you can see the pattern of the text, which fits Samsung eMMCs. So I bought it, and then I tried Command 62 to obtain the firmware, and it worked. And I got a new firmware, and it didn't look like the old firmware I know from Samsung Galaxy S3. There were some function calls which didn't make any sense. I've seen jumps to a middle of a function, but then I noticed this pattern. So this is like a snippet from what I'm doing right now. So I saw that some function calls jump into a middle of a function, which doesn't make any sense. But every time there's such weird call, there's a call to some function right before, which uses for constants OVL0, OVL1, OVL2, and OVL3. And you can see the pattern in the bottom. So every time there's a weird call, there's a function right before. So my guess is this is an overlay mechanism. I think there's not enough ARM memory to store the entire firmware of newer eMMCs. But some functions are stored in a memory overlay. So when you want to call such function, you first load the corresponding memory, and then you call it. And when I dumped the firmware, I had some specific overlay. In my case, it was overlay 2. And all the calls that use overlay 2 make sense, but all the function calls which use different overlays were into like a middle of a function because it's not the correct overlay. So this is a work in progress, and this is what I'm doing right now. I'm trying to see if there's anything interesting I can do with it. So what I'm thinking about is like understand how new eMMCs work, and maybe UFS devices, which is the bus that replaced eMMC bus. And the next thing I want to do is to restore data, because right now I know how to format eMMCs and like, bring them back to life, but I don't know how to extract the data that is on the eMMC chip itself. So this requires to write some FTL metadata parser in order to understand what is stored inside the chip. And the last goal, like the ultimate goal that I wish to see, is some open source alternative firmware. So you could buy an eMMC chip, which runs some code that you maybe don't trust, and then flash it with a new firmware, which you can see the source code, and then it will work. So to conclude, I can own Samsung eMMCs. I can fix bricked S3 devices with software only, you don't need to have any special hardware. And this is just a use case. You can basically do some other things with eMMCs. And newer eMMCs are probably still susceptible to this backdoor. A few shoutouts. So Rebellos, Adam Atler, and RadekDev did all this external SD card work. They actually found out that the Exynos boot ROM allows you to boot from an external SD card. Entropy 512 was involved in the eMMC research back in 2013. And Bani Exobs held a talk at CCC some years ago about hacking Chinese SD cards, and they actually mentioned my research, which was still new, and they basically motivated me to finish it. So yeah, thanks. And you can find all the code that I used in these links. The first link is the SBoot exploit, shellcode, and eMMC-related stuff for Samsung Galaxy S3 devices. The second link is the slides. And the third link will be released later. It's a Python tool that I wrote to experiment with eMMC devices. It allows you to dump the firmware and do some other things. So it should be online in a couple of, like, this week or so. So thanks.